Designed for additive manufacturing. Optimization of 3D printing process parameters. Process parameters. Layer height. This affects resolution, surface finish, and printing time. Thinner layers offer finer detail, but take longer to print. Infill density. This determines the amount of material used to fill the interior of the model, impacting strength, weight, and material usage. Printing temperature. This affects material flow, layer adhesion, and potential warping. The optimal temperature depends on the filament material. Printing speed. This influences printing time and quality. Slower speeds allow for better layer adhesion, but take longer. Cooling settings. Proper cooling helps solidify the printed layers, minimizing warping and improving dimensional accuracy. Optimization techniques. Trial and error. This involves manual adjustments and printing tests to observe the effects. While effective for gaining experience, it can be time-consuming and resource-intensive. Design of experiments, DOE. This method uses a statistical approach to plan and analyze experiments, identifying the optimal combination of parameters for desired outcomes. Machine learning. Advanced algorithms can analyze past printing data and recommend optimal parameters based on user-defined goals, e.g., strength, surface finish, printing time. Factors to consider. Desired outcome. What property is most important for your print, e.g., strength, aesthetics, printability? Material properties. Different materials have varying optimal parameter ranges. Refer to manufacturer recommendations. Printer capabilities. Each printer has limitations in terms of supported parameters and materials. Software features. Some slicing software offers built-in optimization tools or recommendations based on user input. Important points. Start with a baseline set of parameters based on the material and printer recommendations. Make small adjustments to one parameter at a time while keeping others constant to isolate its effect. Document your experiments and results for future reference. Machine preparation and settings. Machine. Physical checkup. Cleanliness. Wipe down the print bed and surrounding area to remove any dust or debris that could interfere with adhesion or cause imperfections. Filament path. Ensure the filament path is clear and free of obstructions. Check for any tangled or broken filament remnants. Nozzle check. Briefly preheat the nozzle and visually inspect for any clogs or damage. If needed, perform a nozzle cleaning procedure as recommended by your printer's manual. Build plate leveling. This step is critical for ensuring consistent layer adhesion. Follow your printer's specific instructions for leveling the build plate, which often involves adjusting screws or knobs to achieve a level surface across the entire area. Material loading. Choose the right filament. Ensure you're using filament compatible with your printer and suitable for your desired print outcome. Load the filament. Refer to your printer's instructions for the specific loading process. This usually involves preheating the nozzle to the recommended temperature for your filament, then feeding the filament through the extruder until it reaches the nozzle. Settings. Slicing software. Most 3D printers rely on slicing software to convert your 3D model into a series of instructions for the printer G-code. Choose a slicing software compatible with your printer model. Import your 3D model. Import your model file, e.g., STL, OBJ, into the slicing software. Configure settings. Print profile. Select a pre-configured print profile based on your filament type and desired print quality, e.g., draft, standard, high quality. This profile will provide baseline settings for various parameters. Adjust parameters. You can fine-tune various parameters based on your needs, such as layer height, affects resolution, surface finish, and printing time. Infill density. Influences strength, weight, and material usage. Printing temperature. Optimizes material flow, layer adhesion, and minimizes warping. Printing speed. Balances printing time with quality. Support structures. If your model requires support for overhanging features, enable and configure the support settings. Generate G-code. Once satisfied with the settings, generate the G-code file that will be sent to your printer. Transferring G-code. Depending on your printer model, you might be able to directly transfer the G-code file via USB, SD card, Wi-Fi, or cloud connectivity. Refer to your printer's instructions for the recommended method. Print startup. Load the G-code. Load the generated G-code file onto your printer using the chosen method. Preprint check. Double-check the print bed is level, filament is loaded, and all settings are accurate. Start the print. Initiate the printing process on your printer and monitor the progress to ensure everything runs smoothly. Design rules for 3D printing. Wall thickness. The minimum wall thickness for a part should be greater than the diameter of the nozzle used in the printing process. This is because thin walls are more likely to warp or break during printing. Overhangs. Overhangs are features that jut out from the main body of the part. They require support structures to be printed underneath them, which can add to the printing time and cost. It is best to minimize the use of overhangs in your designs. Holes and gaps. The minimum size of holes and gaps in a part will depend on the type of 3D printer being used. Smaller holes and gaps may not be printable or may not come out clean. Draft angles. Draft angles are the angles of the sides of walls and other features in your design. Parts with no draft angles can be difficult to remove from the printing bed. It is recommended to use draft angles of 5 to 10 degrees. File format. 3D printing files should be saved in a format that is compatible with your 3D printer. Common file formats for 3D printing include STL, OBJ, and AMF. Part quality, layer height, line width, etc. Several factors influence the quality of a 3D printed part, including layer height, the thickness of each layer deposited during printing. Line width, the width of the extruded filament or material line. Infill density, the percentage of solid material within the part's interior. Printing temperature, the temperature at which the material is melted and extruded. Print speed, the speed at which the printing head moves. Support structures, additional material used to support overhanging features. Impact of layer height. Lower layer height. Advantages. Improves surface finish, higher resolution for fine details. Disadvantages. Increases printing time, weaker parts due to weaker layer bonding. Higher layer height. Advantages. Faster printing time, stronger parts. Disadvantages. Rougher surface finish, lower resolution for fine details. Impact of line width. Thicker line width. Advantages. Faster printing, stronger parts. Disadvantages. Lower resolution, poorer surface finish. Thinner line width. Advantages. Higher resolution, better surface finish. Disadvantages. Slower printing, weaker parts due to potential gaps between lines. Part shell, wall thickness, top/bottom thickness, bottom pattern, initial layer, etc. Part shells and considerations. The outer walls defining the shape and providing structural integrity to the printed object. Key shell parameters. Wall thickness. The thickness of the part's walls, directly impacting strength and material usage. Top/bottom thickness. The thickness of the top and bottom layers, influencing structural stability and surface quality. Bottom pattern/initial layer. The pattern used for the first layer of the print, affecting adhesion to the print bed and surface quality. Example. An engineer designing a phone case prioritizes strength and structural integrity. They choose a thicker wall thickness throughout the case and a thicker bottom layer for stability, accepting a slightly longer printing time. The initial layer uses a grid pattern for optimal bed adhesion. Key shell parameters. Wall thickness. Factors to consider. Part functionality and purpose. Thicker walls are stronger, but use more material. Chosen AM process. Different processes have limitations on minimum and maximum achievable wall thickness. Recommendations. Follow the minimum recommended wall thickness for your chosen process. Use thicker walls for structural parts and areas experiencing higher stress. Consider using variable wall thickness for complex geometries, optimizing strength and material usage. Top/bottom thickness. Impacts, structural stability, surface quality, printing time. Recommendations. Use thicker top/bottom layers for parts requiring higher stability. Balance thickness with printing time and material usage. Bottom pattern/initial layer. Options. Various patterns like grid, concentric lines, and brim. Impacts. Adhesion, surface quality, printing time. Recommendations. Use a brim for parts prone to warping or curling. Choose a pattern that promotes good bed adhesion and surface quality. Part infill, infill density, infill pattern, infill support, etc. Part infill and optimization. Infill, the internal lattice structure within a 3D printed part, impacting weight, strength, and printing time. Key infill parameters. Infill density, the percentage of solid material used to fill the part's interior. Infill pattern, the geometric design of the infill structure, influencing strength and material usage. Infill support, additional infill used specifically to support overhangs and specific features. Example, a designer creates a gear requiring strength and some weight reduction. They choose a moderate infill density with a gyroid pattern, known for its good strength-to-weight ratio, and use support structures for areas with overhangs. Infill density impacts weight, strength, printing time, material usage. Recommendations: use lower infill density for lightweight parts or aesthetics. Use higher infill density for stronger parts or functional applications. Consider variable infill density for specific areas requiring different strength levels. Infill pattern. Common options: rectilinear grid, gyroid, honeycomb, triangles, cubic. Factors to consider. Strength requirements. Some patterns offer better strength in specific directions. Material properties. Certain patterns work better with specific materials. Printing time and material usage. Complex patterns may take longer to print and use more material. Recommendations: experiment with different patterns to find the best balance for your needs. Infill support. Purpose: provides temporary support for features like overhangs that cannot self-support during printing. Options: can be the same or different pattern from the main infill. Recommendations: use infill support for overhangs and features requiring additional support. Adjust support density and pattern based on the complexity of the overhangs. Material characteristics, printing temperature, flow rate, diameter, etc. Material selection. Choosing the right material is crucial for successful 3D printing and achieving desired part properties. Key material properties. Printing temperature, the temperature at which the material melts and becomes suitable for extrusion or other deposition methods. Flow rate, the speed at which the melted material flows through the printer nozzle. Diameter, the diameter of the filament or material used in the printing process. Strength and stiffness, the ability of the material to resist stress and deformation. Heat resistance, the maximum temperature the material can withstand without deformation or degradation. Chemical resistance, the ability of the material to resist the effects of various chemicals. Example, an engineer printing a functional prototype for a high-temperature application selects a heat-resistant material like Ultim. They adjust the printing parameters, including nozzle temperature and flow rate, based on the material's recommendations to ensure proper printing and achieve the desired heat resistance in the final part. Printing parameters, settings on the 3D printer that influence how the material is deposited and affect the final part quality. Common printing parameters. Nozzle temperature, directly related to the material's printing temperature, ensuring proper melting and flow. Print speed, the speed at which the printing head moves, affecting layer adhesion, surface finish, and printing time. Flow rate, the speed at which the melted material is extruded from the nozzle, influencing line width and overall part density. Printing speed and revel. Printing speed, the speed at which the printing head moves to deposit material, impacting printing time, surface quality, and part strength. Impact of higher speed. Advantages: reduced printing time, increased productivity. Disadvantages: lower surface quality, weaker layer adhesion, increased raveling risk. Impact of lower speed. Advantages: improved surface quality, stronger layer adhesion, reduced raveling risk. Disadvantages: increased printing time, decreased productivity. Revel, the unwanted curling or fraying of filament or material at the edges or around holes during printing. Factors contributing to revel. High printing speed. Faster movement can cause the material to stretch and curl before solidifying. Material properties. Some materials are more prone to raveling due to their inherent flexibility or moisture content. Nozzle temperature. Incorrect temperature can affect the material's flow properties and contribute to raveling. Retraction settings. Improper retraction settings can cause the filament to ooze and form strings during travel moves. Minimizing ravel. Reduce printing speed. Slower speeds allow for better material cooling and solidification, reducing raveling. Adjust retraction settings. Optimize retraction distance and speed to minimize filament oozing during travel moves. Increase nozzle temperature. Within the recommended range, a slightly higher temperature can improve flow and reduce raveling for some materials. Experiment with different materials. Choose materials with lower raveling tendencies when possible. Example. A hobbyist printing a decorative vase prioritizes smooth aesthetics. They choose a slower printing speed to minimize raveling and achieve a cleaner surface finish, accepting a longer printing time. They also experiment with retraction settings to find the optimal balance for their chosen material. Post-processing. Post-processing. Additional processes applied to 3D printed parts after the printing is complete, aiming to improve aesthetics, functionality, and overall quality. Selecting the right technique. The choice depends on the desired outcome, material type, and complexity of the part. Example. A designer creates a prototype for a consumer product requiring a smooth, professional finish. They remove support structures, sand the surface, apply primer and paint, and finally polish the part for a high-quality appearance. Common post-processing techniques. Support removal. Removing the temporary structures used to support overhangs during printing. Sanding and smoothing. Using sandpaper or other tools to smooth the surface of the part and remove layer lines. Chemical treatment. Applying specific chemicals to improve surface finish, enhance bonding for painting, or achieve specific effects. Priming and painting. Applying primer and paint to enhance aesthetics, improve durability, or add functionality. Vapor smoothing. Exposing the part to solvent vapors to melt the surface slightly, creating a smoother finish. Polishing. Using polishing techniques to achieve a high-gloss finish for specific applications. Machining and finishing. Utilizing traditional machining techniques for high-precision dimensional accuracy or intricate surface features. Technology-specific parameters. Technology-specific parameters. Understanding the nuances. Different 3D printing technologies have unique characteristics and require specific parameters for optimal results. Importance of knowledge. Familiarity with technology-specific parameters allows for optimized printing, achieving desired part quality and functionality, reduced errors and waste, minimizing printing issues and material usage, efficient printing process, streamlining printing workflows and maximizing productivity, learning resources. Consult user manuals and documentation for specific 3D printer models. Research online resources and communities dedicated to different 3D printing technologies. Experiment and keep records of successful settings for future reference. Example. An engineer working with FDM understands the importance of nozzle diameter and adjusts it based on the desired layer height and surface finish. They also experiment with different retraction settings to minimize stringing for their chosen material. This knowledge allows them to achieve high-quality prints efficiently. Common technologies and key parameters. Fused deposition modeling, FDM. Nozzle diameter. Affects layer width and resolution. Print temperature. Crucial for proper material flow and adhesion. Build plate temperature. Influences warping and bed adhesion. Retraction settings. Minimizes filament stringing during travel moves. Stereolithography, SL. Laser power and scan speed. Impact layer thickness, surface finish, and cure depth. Resin viscosity. Affects flowability and layer adhesion. Support structure parameters. Crucial for delicate features and overhangs. Selective laser melting, SLM. Laser power, scan speed, and hatch spacing. Determine melting depth, surface finish, and mechanical properties. Powder layer thickness. Influences resolution and overall part size. Support structure design. supports complex geometries, and minimizes residual stress.